I have slightly expanded the topic to cover the whole of North America for reasons which will become apparent very shortly. So there's really a number of questions that I hope to answer in this talk. First of all, what do we mean by shale oil and tight oil? Secondly, just how much and how large is that tight oil production at the present day? Where is it coming from in North America? Why have we seen this rapid production increase? Because you will see one. And finally, what impact has that shale oil and tight oil production growth had to date? Are there any constraints on future growth? And what is the likely future impact? So to start with, what do they mean? Well, actually, the US authorities tend to regard tight oil or embrace shale oil within tight oil, and they simply mean oil that is in a rock which is relatively impermeable. That's what they mean by tight, relatively impermeable. Shale is impermeable, but I will try and use a slightly different classification and split the two of them. So I looked at the attendance list and I noticed that you're not all petroleum geologists. So I just want to say a little bit about what we mean by shales and tight and words like that. First of all, this is exactly not what we're talking about. These are oil shale bings, and if you drove from the west to Edinburgh today, or maybe even if you landed by plane and looked out the window, you'll have seen things like that. And what you're looking at there is the oxidized residue of the world's first large-scale hydrocarbon industry. The Scottish oil shale industry produced about 60 million barrels from about the 1850s onwards until it came to a halt in the 1960s. And now oil shale is rock that contains insoluble organic matter. We call it kerogen, but you can just think of it as big, really big organic molecules. And to produce that oil, it was retorted until oil was driven off by heat. In reality, in nature, and over geological time, nature does that for us. Nature is the, if you like, the natural oil refinery. Temperature takes the inorganic molecules that are deposited on the seabed or on a lake bed, on the bottom of a swamp, and as it's buried and the temperature rises, nature breaks down that inorganic material in exactly the same way as a refinery does. And depending on the original source material, you end up with different things. So if you take the algae, for example, that you get in a lake, you will end up with what's a particular type of oil that's rather waxy and not particularly rich in gas. If you take the marine plankton that descend and filter through the sea and lie on the seabed and are eventually buried, they will create oil and gas, a mixture of the two. But land plant material tends to create a very gassy final product. And if it's concentrated enough, of course, instead of it just becoming gas, it will become coal. There are some, in addition, of course, if you take oil of whatever source and you heat it enough, eventually that natural refinery will break down those longer molecules, first into the liquid molecules and eventually into the gas molecules down to the purest one, which is CH4 methane. So that's what we're looking at here. Once that's happened, once the source rock of the inorganic material, that the oil has been generated within it, it is then sometimes expelled, and it moves through carrier beds either to a reservoir, let's say, the rock that we conventionally produce oil from, which is both porous to hold the oil and permeable so that it can flow through it. Sometimes it will come right to the Earth's surface, and you'll see it as oil seeps. They're very common in the bottom of the Gulf of Mexico, for example. Sometimes it will accumulate, but then there will be erosion and it will be breached and the light oil will disappear and all you'll be left with is the heavy bitumen of the Athabasca tar sands, something like that. But the process is actually very inefficient, the expulsion process. And a lot of it remains behind in that original source rock, because once the pressure differentials that allow the oil to migrate dissipate, it's hard for that oil to get out of the source rock. So there's a lot of stuff still remaining behind in that original source rock. So when we talk about unconventional oil, unconventional resources, these are some of the things that we're talking about. There's really two types of occurrence. The unconventional trap, it's sometimes called a resource play or a geostratigraphic play. It's continuous over a large area. It's not really affected by the buoyancy of oil or gas in water because it's very tight and doesn't migrate very well. And of course, a shale isn't exactly that situation too. So you get tight oil or shale oil in unconventional traps. The other kind of unconventional oil is unconventional production. And that, when the term unconventional was first used way back in 1968 by the US government, it was to encourage production from difficult reservoirs. And once again, these difficult reservoirs are basically the tight reservoirs where you need some exceptional technique in order to get that oil and gas out. And of course, this was reflected initially in the economics of recovery. These were uneconomic, and so tax advantages were given to encourage unconventional production. So if we look at the first one, this is essentially both tight oil and shale oil, but this one is, broadly speaking, tight oil. It can be summarized too in this sort of, if you imagine, for example, here's a kerogen-rich source rock. The deeper it goes and deeper it's buried, first of all, oil forms and then shale gas forms. Conventional accumulations often occur because of the buoyancy of oil and gas on the water that's moving through here at the crests of anticlines and fault blocks. Now, over geological time, a rock that is tight and very impermeable, oil and gas will still accumulate in it. And you may find that, for example, in a conventional trap, like this, that the reservoir is tight. It's accumulated over geological time, but you can't produce it over useful human time. So it's still, although it appears to be conventionally trapped, it's still a tight reservoir as far as the technology is concerned. So, on the upside, what are the advantages of shale oil and tight oil? Well, the exploration risk is low. I mean, if it's a shale source rock that's widespread over a large area, you know exactly where it is. It's not difficult to find. The reserves are developed over a long period of time, and the production tends to be stable and predictable. The actual evaluation of the size of the resource is done as part of the development drilling process. So it's assembly line development, stepping out from a known well to the next well, etc., etc. And the plus about that long project life is it provides an opportunity to improve recovery and to improve efficiency and security of supply. And it's what Peter Jackson was saying this morning. You can't imagine that medical technology is now just suddenly going to stop where it is today. Well, exactly the same is true of oil production technology. When you've got that long-lived resource, you can develop the technology and improve it over time. There are downsides, however. The recovery factors for shale oil and tight oil are very low, and there's a reason for that. If you look at the conventional anticlinal accumulation in a porous, permeable rock, you can inject water down beneath it and push the oil up and push it towards the well bores, water injection. But the very last thing that you want to do is to shove water into a fractured shale, because you're just going to keep it there. The only driving mechanism for oil from shale is the expansion of gas on pressure release as you drill the well, of the associated gas that drives the gas towards the wellbore. And that's why it's that particular kind of marine source rock that is particularly good, because it's got the mixture of non-waxy oil and the associated gas that's driving the oil towards the wellbore. In shale gas, just as an aside, actually oil is an impediment. Oil stops that shale gas migrating to the wellbore. But in the case of shale oil, gas is actually a help. It's what pushes the oil towards the wellbore. Another problem is that you can only exploit a very limited area around a wellbore. So in other words, you have to drill a very large number of wells and therefore have a high well density in order to recover a lot. The costs are high, as we'll see. There's a lot of technology involved. Completing these wells may involve having significant amounts of water required for the fracturing process, and there is the potential for groundwater contamination, and we're all familiar with all of those sorts of discussions. So let's look at the history of US oil production. This is the very first well that was drilled deliberately for oil that actually found oil. Many oils had been drilled for hydrocarbons before the Drake well in Pennsylvania, but they were shale gas wells, and the oil wells that were successful oil wells were largely saline brine wells that accidentally discovered oil. So back in 1859, the US discovered oil and started to produce it. And everything went along happily for about 100 years. Only onshore oil produced in the lower 48 states. And then at the beginning of the 50s, people started to explore offshore and on the continental shelf of the US. That was followed, as the search for oil continued, by looking at a completely new territory, Alaska, where the Prudhoe Bay field was found in 1968 and came on stream about 10 years later. In the ongoing search for oil, the next thing to do was to look in the deep water of the Gulf of Mexico. And by deep water, the US means water depths of over 1,000 feet. And everything was going pretty swimmingly there as well until in 2010, the Deepwater Horizon blowout caused a knock-on effect and reduction in activity. And so there was a bit of a decrease in deepwater exploration from that point onwards. If we look at onshore exploration, excluding three fields, which are three areas that I'm going to talk about in a second, we'll see that it peaked in about 1970, and by 2006 it had dropped to a level that was last seen in 1938. In other words, a major decline in onshore production. But there is an increase from that point onwards, and I'll explain in a minute what that is. But if we look at the three particularly impressive rocks for various reasons, the Bakken, the Barnett, and the Eagle Ford, adding the combined shale and tight oil production from those areas raised US production to a level last seen in 1995. The Bakken and the Eagle Ford are two prolific sources. I put the Barnett in because it's interesting. It was the first shale gas exploration target that discovered shale oil and gradually started to produce shale oil from what had primarily been a shale gas exploration play. The word play will come up occasionally. A play is a sort of a mode of occurrence of hydrocarbons. It's a word geologists use that it can be a generalization, the structural faulted structure trap or play, or it can be refer to a rock type like the Bakken play. It's just a bit of geology jargon. So if we look at those two particular prolific zones, first of all, the Bakken Three Forks oil production area, you will see that the reason for the change in the title of the talk, this one actually straddles, it's in the Williston Basin, which straddles the US-Canadian border. And in fact, production has come from this Bakken, and it's a tight oil situation. It's two shale source rocks with a very, very tight siltstone sandstone lying in between, and that's where the production comes from. And it has produced since 1953 in North Dakota, but the major production only started with the discovery of the Elm Coulee field in Montana. And first of all, it rose there, it's plateaued since, and then thereafter, North Dakota is the area that's really taken off. And by the end of last year, production was getting close to 750,000 barrels a day, and close to 1 billion barrels had been produced. It isn't stopping. If we look at both the North Dakota Bakken alone and the Eagle Ford in Texas, you will see that in the first quarter of this year, production has continued to soar. The Eagle Ford has now reached half a million barrels per day, and the Bakken is now at, in Dakota alone, is now at 700,000. And why is it happening? Well, it's happening not out of altruism and to stop US import oil. It's happening because you can make money from it. And in fact, it has been said that at a break-even price of $19 for West Texas Intermediate, which is the US benchmark crude, a well here is a license to print money, and clearly it is. There are many other plays, and this is the cause of the other upturn in the US production that I referred to, other than the Bakken and the Eagle Ford, because production from several other shale plays also started to increase from about 2008 onwards. And if you look at where they are, a lot of them are in the Texas Permian Basin, which is in West Texas. The Eagle Ford is also largely in West Texas. The Bakken is the one that straddles the Canadian border. These ones there that say things like the Niobrara, they're in the eastern edge of the Rockies largely. And then there is one very large play, the Monterey Shale, except it's not really very much a shale. But it's the source rock for almost all of the oil in California. And it's the play that the US Energy Information Administration estimates will actually ultimately produce the most shale and tight oil in the US. Total production by December was 2.2 million barrels a day. Turning to Canada, this is the total tight oil production. It was 160,000 barrels a day in 2011. The Manitoba and Saskatchewan production is largely that Bakken oil production on the Canadian side of the border, but there's also tight oil production from Alberta. And by the end of last year, it was close to 300,000 barrels a day. So we're looking at a total 2.5 million barrels a day of tight oil and shale oil production in North America. So how has this come about? Well, it's actually not just it's not really a revolution, it's evolution. It's actually the application of new technology to old techniques. Techniques that have been going around for a long, long time. The first well to be fracture stimulated was actually fractured 2 years before the first oil well was drilled. It was a shale gas well in upstate New York. And I like this picture because I wonder what's in the mind of the three guys standing at the back. Are they sort of saying, would you stop looking at the camera and watch where you're pouring that nitroglycerin? But it does say something about how fracturing originally took place. It was a case of shattering the rock. And you can still pick up a copy of The Guardian and read something about fracking and so on, and it'll talk about shattering rock. But the present-day process of fracture stimulation isn't like that at all. It's hydraulic fracturing. In other words, forcing apart, injecting water under pressure with little proppant, sand grains or ceramic balls to keep these fractures open, and forcing the rock apart either using natural fractures that already exist and expanding them or creating new ones. And so basically the process is one of taking a well bore and injecting at selected points and creating those fractures. It's that simple. And it's been commercial in the US since 1949, in Canada since 1953. The first attempt to fracture a shale was in the Appalachians in 1976, but the first commercial shale gas fracture programs were in the Barnett Shale in 1998. And this is basically what an operation looks like. It's busy. The wellhead is actually that little red thing there. But you can see you need an awful lot of trucks to bring all of the material to the fracturing operation. And for example, the Apache Horn River 10 frac requires 2.4 million kilos of sand and 32 million liters of water. Nowadays, they are doing 40 frac jobs, in other words. So you can see the volumes that are actually required. Here's some of the other technologies. Horizontal drilling is a key one. As you will have noticed in that one before, the well bore was horizontal, not vertical. The plus about horizontal drilling is that shales in particular are very heterogeneous, and so you can never be sure where the productive bit is going to be. But if you fracture 40 times, the chances are that you're going to hit something good somewhere along the way. So nowadays in the US, they're drilling horizontal legs of 10,000 feet, 2 miles basically, and fracturing them 40 times. But it's an old technology, it goes back to 1929. Multilateral wells. This happens when you actually drill two parallel, same vertical well bore, two parallel wells either above each other or splayed out like that. You need to know where you're going when you're doing all of this, and you don't want to pull the drill string out all the time to log it. So techniques like measurement while drilling and logging while drilling are important. And finally, real-time seismic monitoring. Again, a 1970s technology, but what they do is they have geophones when they're fracturing, and they can tell just exactly how far the fractures have penetrated and when they want to stop so that they don't fracture out of the productive zone into something else. So these are all old technologies. When people say it's all new and it's frightening, in fact, it's all really old, but it's just being developed a bit further. So let's look at what the impact has been. Here at the bottom, this is the crude production from the Eagle Ford and the Bakken. You can see that it broadly parallels the production up there from the increase in overall US production. There's just about the same difference here and here. That little extra lift there has come from the other 8 plays that I mentioned earlier. But what is the important thing to note is that the consequence of that has been that there's been a major decline in US crude oil imports. And there have been another number of consequences. The tight oil is a light oil. It's a sweet oil. By sweet, we mean it's low in sulfur. And because that has been produced, but it's being produced, for example, the Bakken is in the Rockies. It's got to be shipped out of there by rail. There are no major pipelines taking that. So there's the price has been discounted relative to other benchmark crudes. So, for example, in 2008, West Texas Intermediate, the US benchmark, was traded at a premium to Brent, the international premium. By 2012, West Texas Intermediate was trading $15 a barrel less than Brent because the shipped international could access the refineries a lot more easily than the tight oil from the Rockies. The consequence of that was it incentivized refiners to process light, tight, sweet oil. And so the major decline in the imports was in sweet crude imports. And since July 2011, product exports of products from the US have exceeded the imports for the first time in over 60 years. So it has had a major impact on the US economy in a whole range of ways. Just to look at, finally, some of the constraints. This is one of the problems is that the decline rate is very, very rapid for the first 3 or 4 years, after which it becomes actually very, very gradual, and a typical Bakken well is estimated to have a 45-year well life and to make something like 20 million of net profit. So it will go on even beyond that. But you can see that in order to keep production stable, you have to keep drilling wells very, very rapidly. So, what are the constraints? Well, rig availability is one of them. Once you've drilled up those sweet spots, more rigs are required to maintain production levels. Getting rid of that water once you've fracked it and it comes back to the surface is also a problem. Are there enough crews? Is there access for rigs and completion? For example, in the Bakken in April, 80% of roads were impassable because of April blizzards. So there are restrictions like that. And there is still, at the present time, a problem of getting the oil from the production to the refineries. And then we have all of the societal choices that we well know about. It's hard to know how much there is because there are various estimates and many of them are not particularly compatible. The Energy Information Administration reckons that in tight oil reservoirs there's about 47 billion barrels of technically recoverable oil, that takes no account of economics. Shale gas reservoirs contain more and tight gas reservoirs other. The USGS has only assessed some of these, and its estimate is something like 13 billion barrels plus another 3 of natural gas liquids. In Canada, you can see the challenge here. In Alberta shale oil alone, the Energy Resources Conservation Board of Alberta estimates over 400 billion barrels of oil, whereas the technically recoverable shale oil that the recoverable from that, the EIA estimate 8.8. And going with that actually is a figure of 160 billion barrels in place. So in other words, almost 3 times less than the Albertans estimate. But bring it down to actual reserves, and these are the actual reserves, proved reserves figures, and it's 500 million barrels in Canada. So from that technically recoverable, again, just a small fraction. And the production future, they estimate, will peak in around about 2020. That's the EIA's estimate at the present time, and then tail off gradually. And finally, can this success be reproduced internationally? And Lord Oxborough said, as he said, it's not just about the geology, it's actually about some of the other positive advantages that you have in North America, which include private ownership of subsurface rights, a truly competitive business environment in which only the efficient and the cost-effective survive, the fact that you've got a large number of suitable drilling rigs and a good pipeline gathering infrastructure and availability of water resources. And people seem to think that water is an issue, but I mean, just to give you an example, if in the back end of North Dakota in the next couple of years they fracture 5,000 wells, that will lower the level of the lake, which is the principal water source, by 1 inch. So the water resource is not an issue. So thank you very much. Happy to talk to you all later, and if that's not suitable for you, please send me an email.